Hi, I'm Ryan Daws, editor at TechForge Media, and with me today is Rob High, the CTO of Edge Computing at IBM. So Rob, can you give us a quick update on some of IBM's latest work in edge computing?
Yeah, so we've been working, we continue to work on our use cases around Industry 4.0, things like production quality, worker insights, production optimization, bringing AIs into these environments, using visual inspection and visual analytic to be able to recognize, when parts are not correct when they're being assembled, or actually more recently, we've been doing some work with robotics on recognizing facilities and facilities maintenance problems, whether or not equipment's in the right place and whether it requires maintenance or any kind of supervisory support for fixing the situation. So, a lot of use cases, a lot of utility in other industries, going now into retail, into the automotive industry. We're seeing lots of examples of where people want to be able to use the advantages of having compute local to where they're doing their work and facilitating them, lowering their latency, protecting their personal private information, managing the cost of all the data they're producing.
Yeah, you mentioned AI there, and just today, as of filming, IBM announced a new £210 million Centre for AI and Quantum Computing Research in partnership with the UK's Science and Technology Facilities Council. You were, of course, the former VP and CTO for IBM Watson. So what are the benefits of Edge AI?
Well, when we think about AI, we like to think of it more, not so much as artificial intelligence, but more as augmented intelligence, which is the idea that AIs will benefit humans in the way that we think, the way that we imagine, to help us kind of think about the things we weren't thinking about when we think about it on our own. Mm-hmm. And so AIs, are best when what they're doing is helping us make better decisions. To be able to do that, the machine has to have a really engaging experience with us. It has to activate, our imagination. It has to activate our ability to be inspired. And if you think about it in human terms, what are those things that cause each other to be inspired by the things that we say? It's not just simply the words that we use, it's how we express that. It's how we, sometimes don't answer a question, but answer a question with another question, for effect, for the benefit that brings to cause us to think things through. But that requires very low latency interactions. I mean, as human beings, we're influenced by, the things in our context, in our environment on a sub-millisecond level. The dilation of pupils is something we're barely conscious of, but in fact, it influences, our own reaction to each other. When somebody's eyes or the pupils are dilated, that's a indication that the person's engaged. They're thinking. They're really concentrating on what the other person is saying, and that little cell of cue gives the other speaker a sense that who they're talking to is following what they're saying. So that's really necessary. That very very subtle, very minute, fine-grained interactions are what influence humans and cause us to be inspired. And so the coupling between AI and human interaction is dependent upon having very low latency interactions. Of course, that also requires that the AI have an acute understanding of the context in which we're operating. So even things as subtle as the movement of things behind us, when we both experience that movement, that is a shared experience that informs the way that we interact with each other. And so collecting up even some of those background activities can improve how AIs interact with human beings. And finally, there's a lot of data involved, and transmitting that data, from wherever we are, whether we're in the office or we're in the factory, or whether we're in our car or in the retail store, transmitting all of that data, all that context, all that environmental information, and of course, even just the stream of data that is our communication to begin with, can be quite expensive. So if we reduce the latency, so we can reduce the amount of bandwidth demand, if you can get that processing occurring in the context in which we exist, then AIs can actually do a better job.
Well, I very much hope that my pupils are deleted now. I believe they are. I am listening.
Well, we're all going to be much more conscious suddenly.
So IBM is, of course, one of the world's leading vendors in facial recognition technologies, and last year took a quite firm stance against the use of facial recognition for mass surveillance, racial profiling, or any other violations against basic human rights and freedoms. Can edge computing help to address some of those concerns while still unlocking the technology's full potential for beneficial use cases such as speeding up plane boarding and tackling serious crime?
It's not just facial recognition. I mean, we're all kind of have lots of information about us that we consider to be either personal or private. And maybe it's not even just about the individual. Sometimes it's just about, the business in which we are participating. On the factory floor, for example, if we have cameras that are being used to recognize not people, but rather the quality of the work that's being performed by the machines on that floor. If we've got a camera looking at, the parts coming off an assembly line and testing for whether they're, the welds are being performed properly and so forth, but yet that same image is now picking up information in the background, whether those are people or perhaps even just simply the state of the production process itself, that's valuable and sensitive information. Mm-hmm. For somebody else to be able to come in and capture that information could help them understand whether their competitors are, in a better position or a worse position to be able to produce, the work that they've been contracted to do and so forth. So I could tell you a lot from a competitive standpoint about the competitive situation, economic situation that the competitors are in. So for all these reasons, moving that data around only creates further exposure. The less movement, the more that you can kind of keep that data right where it was captured, whether those are, information about humans, information about your business, information about the environment in which your business operates. You don't want that data moving around any more than it has to. So if you can move the analytic to where that data is being captured, even right there on the camera itself, mm-hmm. right? Perform the analytic, draw the inferences that you're going to from that, but then throw the data away, throw the imagery away or whatever else has been captured, then you've actually improved not only the personal and private information that that we all are very sensitive to, but also any confidential information that may be about the business that we're operating.
And I guess it's more recent hardware advancements that's enabled that processing, as you said, actually on device.
I mean, almost all the devices that we are accustomed to using, and sometimes not even aware, that these devices have compute, are now more often being built with compute. It's what we call software-defined products. Whether it's even the things that are in front of me right now, this light, this microphone, this camera, all of these things actually have compute in them now. And more often that compute is using general purpose, commodity hardware, x86 chips and ARM chips, and so they're quite capable. And whether that's in the office or that's in our factories, all of the factory equipment, the industrial robots and the stackers and the sorters and the assembly machines and the fabrication machines and all the things that we typically think of as being OT, operations technology. Sometimes that same OT now is being built using IT, information technologies. But that ability to bring software to that device kind of unlocks its features, its functions. It kind of enhances its value by being able to update the software running on it. And that idea, I think, has a lot of power. But that's occurring all around us all the time now.
Yeah. One of IBM's most interesting projects is the Mayflower fully autonomous ship. How is its voyage going, and have you learned anything from that project so far?
Pending, weather conditions, it will be should be launching just about any day. In fact, if you want to kind of monitor its progress, you can go to mas400.com, mas400.com, and learn more about the ship as well as where it actually is right now and the progress it's making. But the things I've learned about it, of course, besides being an incredible example of edge computing, it is a vehicle, it's a boat that has compute power on it. It will be performing all of its own navigation decisions once it's launched. It will sail from Plymouth, England to Plymouth, US, and it will be entirely responsible for its own navigation decisions as it progresses. So, it has very sophisticated software on it, AIs that we use to recognize various obstacles and objects in the water, whether that's other ships or boats or debris or land obstacles or even marine mammals, marine life that the vessel needs to navigate around and avoid. So it's got a great deal of compute. It will be doing all this autonomous navigation. There will be no human assistance in that process. So learning how to do that, learning how to deploy that software into that ship to make it viable. But probably even more important is, this is a platform. Mayflower is a platform for scientific payloads. We talk about this. For the marine sciences to advance, we have to collect data. And today the norm is, when you want to collect data at sea, you put a vessel together, you staff it with scientists and sailors and administrative staff and so forth, and you launch it and you send it out to sea for days or weeks at a time, and that's arduous, right? These voyages are dangerous, of course. The ocean is our friend, but it's also a very dangerous environment to have to live in, and of course it's distant, it's lonely. And the weather conditions can also be strenuous. So if you can launch an autonomous ship where it's able to go do all this sampling, sampling the water for chemistry or for phytoplankton, or listening to whale song to be able to keep track of whale populations, all of these things that I think will help us sustain a more viable and healthier planet to live on. The ship can do a lot for us. And so we're learning a lot about how to build these kinds of payloads and the kinds of data that we get when we can launch it. And of course, the benefits of that is all of the marine science that we can advance because of that additional data.
And you mentioned the weather there, which is the perfect thing to mention to a Brit like myself. The weather is, of course, becoming increasingly unpredictable. IBM acquired the Weather Channel in 2016, has been lending its talent and expertise to ensure the service is reliable as possible. One way the company is using edge computing is for mesh network alerts. Can you explain how these work?
Mesh networks, have as a general principle the idea that we can distribute and communicate. We can distribute the communication by decentralizing the points where that communication is initiated. So, we may send an alert, but rather than relying on every cell phone being connected to a cell tower, in some very remote areas, there are no cell towers. You can't really be well connected. So if a phone instead can be connected to another phone that's nearby, and that in turn can be connected to another phone, then you can actually take the cell tower signal that has that notification on it and relay it essentially across a whole series of phones where, if you presume that the population is kind of evenly distributed across an area, they can be serving, making that communication available without every one of those phones being attached back to the original cell tower. So that kind of mesh networking, I think, is while we're using that in the weather system, it's actually a pretty good example of the kinds of communications we're going to begin to see more and more often. We actually see a bit of this even in factories today with 5G. One of the advantages that 5G brings to the table is higher bandwidth and lower latency. Well, to achieve that, you have to be working in frequencies that are higher and higher, very high spectrum frequencies. The problem there, of course, is the higher the frequency, the more it has difficulty penetrating through, walls and boxes and obstacles and whatnot. So if you're broadcasting a very high frequency 5G bandwidth into or a spectrum into a factory location, all the things you have in the factory begin to block that signal, and you create shadows. So there's a technology company that we've been working with called GenXCom, who will take that signal and relay it in a mesh network throughout the factory, essentially covering all of the shadows that might occur if you only had one antenna that you were using to broadcast across the entire room. And
climate change is, of course, one of the biggest issues of our time, and part of the research that Mayflower is conducting. In what other ways can edge computing help tackle that issue?
To really get in a position where we can respond, and not only to the changes that are occurring in our environment, but to change our own behaviors to return the world back to a more sustainable condition, is going to require a lot of information. It's going to require that we have a lot of awareness of what's happening on a very microscopic scale across the entire planet. It's going to require that we have a much finer grained awareness of the impact that we're having in our daily life. The simple things that we take for granted that accumulate into a greater impact are the things that we have to be most aware of, and the behaviors that we need to change most acutely. Well, all that data and all that awareness is going to require a lot of compute. And of course, as I said before, all of the data that we collect, if we had to send all that back to a central compute complex like a cloud or an IT data center, could get quite expensive. You're transmitting lots of data. The data, as much as we have to collect that data, it's still full of noise. There's still more data than we really care. We're only looking for those little pins in the haystack that indicate, something of meaning to these behaviors and the things that we're doing. And so, we don't need to transmit all that data. If we can process and analyze it in the presence of that data and where that data is being collected, we've talked about reducing the potential for, the data being sensitive and being used for nefarious purposes. So keeping the data where it was created, processing it, getting rid of it out of the system so that we don't have that exposure. B, reducing the cost of transmitting it, the networks that you need, the bandwidth you need, the storage, et cetera, that come along with that. C, simply being able to react more quickly, but even more so to be able to react even when all these other things that you might depend on, like the network, might be down. They may not be available to you all the time. So being able to sustain the processing, even when not everything is available to you, when we don't have access to the cloud, for example, because you're in some remote location, or because your network is interrupted as you traverse between locations, et cetera. All of that is really what edge computing is enabling.
Yeah, it's just generally about being able to react to things much quicker. I know one of the most interesting projects I've seen in the IoT space was detecting smoke before wildfires really start to spread and get out of control. And I guess edge computing can just help to react to that much quicker. And like you said, without potentially the need for, if connectivity drops, you can still detect those things.
Well, that plus, if you think about the safety crews that go out to fight these fires, and not only their need to communicate, but also to analyze. They may be out in a forest someplace, way out of range of any sort of wireless network or any other kind of networking capability. So if you're in a command and control center and trying to orchestrate your resources for fighting that fire, you're going to need local compute to do that with. And so you've got both the hopefully detecting the fire before it began so you can preempt it, maybe even do predict the potential for that fire even before it begins to start, so that you understand the conditions where, that fire is even possible and preempt that. But once you're on station and trying to fight the fire, you need compute to be able to do a better job of leveraging the resources and getting the most efficiency and effectiveness out of those resources as you fight that fire.
And edge computing, of course, isn't a brand new concept, with its origins tracing back to the 90s with the content delivery networks. Why do you think there's been such an increase in excitement around the topic in recent years?
Yeah, we sort of see these cycles in information technology. In fact, I'd argue that we've seen the cycle go all the way back to the early 80s when the PC first got introduced, and people had the idea that they could use their PC to do distributed computing, at their desktop. And we saw this idea of client server come out of that. But a lot of these things in the past, have failed for one reason or another. Client server suffered the problem that administrators, IT organizations could not manage the software deployment to these locations. So we saw a reaction to that in a consolidation back to web applications and web computing. Then we saw the mobile computing era come along, and so the utility of having a mobile phone in your hand and putting applications on that became a really attractive idea, which brought us back to another form of edge computing and distributed computing. But again, the issue that people ran into there is that while I can certainly manage getting the apps that I want on my mobile phone because I'm administrating this myself, it's very hard for institutions to make use of that same idea when what they're doing is distributing this compute into their factory or into the retail stores, where there really is no one person at each of the machines that are out there deciding what software to put on it. So these cycles come because there's this yearning, I think, to be able to take advantage of compute local to where we are doing our work. That's, as you pointed out, been around for a long time, but we run into obstacles, and so we retrench. Then once we solve those problems, then people see that need still, and they want to take advantage of that. And so we see another iteration of that cycle. What's interesting to me about that cycle is that, number one, every time we cycle through it, the numbers, get increased by orders of magnitude. In client server days, maybe there were, for any given institution, hundreds or thousands of edge servers that you had to deal with. Maybe in aggregate across the entire world, there was, perhaps, hundreds of thousands of client machines that we had to manage. We got to the mobile computing, already there's 3.25 billion of these, mobile devices out there in the marketplace. Now we get into edge computing, which is sort of the third iteration of that distributed computing model. And we're talking about literally hundreds of billions of edge devices out there. So, number one, the quantities just continue to explode every time we go through these cycles. We do learn something every time we go through the cycle. We learn from our mistakes, and then we see, improvements made that make it more viable. Standards get introduced, things become more consistent and easier to manage. But every time we do this, there's another sort of generation of innovation that comes out of this. I don't think any of us could imagine, how mobile phones would impact our lives, now 13 years ago when smartphones started coming out. The difference between what we knew and imagined then versus what we know now and take for granted, is phenomenal. And I think we'll see that again now going into the edge computing generation of distributed computing. The last thing I'll say, though, is everybody gets a little worried that, edge computing means the death of cloud computing, but it doesn't. That's the other thing we've learned, is every time you see this shift to decentralized or distributed computing, it actually drives more demand on the centralized computing. We saw this with client server, we saw it with mobile computing, and now we're going to see it again with edge computing and cloud. the cloud is not going to slow down. It's going to grow, but we're going to see, accelerated growth in the edge computing side of that equation.
So that's everything from me, Rob. So thank you for coming along to speak to me today, and I look forward to the panel.
Thank you, Ryan. Appreciate that.